Dear colleagues, in this presentation we want to display you the principles of the insulation, how to select it and how it works. Eventually we will learn how to choose the proper thickness according to the different applications. Let's start together. What is insulation for? I know we are familiar with that. Insulation is for preventing heat losses, that is energy saving, and cost first. Insulation we need also for avoiding condensation, that is, dropping of water, and that can be dangerous in some critical areas, for example electric cabinets, and can be simply nasty elsewhere. But insulation is also for safety, preventing burns by people when touching hot or cold surfaces. In this presentation, we want to deepen a little bit and understand how to size it for the different applications: buildings, machinery, and piping. Let's start from the building insulation that is used for walls or roofs. The task is here to reduce the heating demand. The heat lost through the wall is given by such a formula, where Q is the heat loss, A the area of the wall, and U is the heat transfer coefficient due to conduction. Its expression is given by the formula below, where Si and lambda I are the thickness and conductivity of each layer. If they are many, we sum the heat resistance in series. That thermal resistance is proportional to the thickness of the layer and inversely proportional to the conductivity. We want to solve now a problem: how to choose the insulation thickness of a wall to increase the inside temperature of that room by keeping same heating power. If the heating power is the same, we can say that the heat loss before insulation and after is the same, only U and T1 are changing. This equation we can write also as per point 1. And since the inverse of the new U is the inverse of the old U plus S over lambda, where S is the thickness of the new insulation layer, as written at point 2, we can combine 1 plus 2, obtaining the final formula in red for the thickness of the insulation layer. I want to place you a challenging question now. The thicker is the insulation, the more is effective. Let's work out the heat loss equation so that the thickness appears explicitly here. If you represent in a chart the heat loss Q versus the thickness S, we can see that the benefit of the reduced loss is coming smaller and smaller, so that it is not convenient to increase the insulation thickness further. The second argument is the insulation of the machine. Here also is applicable a very similar law. H is the heat transfer coefficient, Tm the temperature of the machine, Ta the temperature of the ambient, and Ts the outer temperature of the insulation. The main difference versus the formula used for a wall is that here the heat transfer coefficient is made of two parts, one due to conduction and one due to convection and radiation. On that purpose we need to introduce a new coefficient small h. The heat loss appears like in the formula number 1, where delta T is considered between the machine surface and the ambient. The heat loss only due to convection appears like in formula number 2 instead, where Ts is the temperature of the outer surface of the machine, therefore with insulation, and Ta the temperature of the ambient. Combining both equations, we get an expression in red saying how much is the thickness to achieve a wanted surface temperature Ts. The heat loss before and after the insulation we can calculate by using the same formula, just with different values of the heat transfer. In the first case, using the convection and radiation coefficient small h prime, and with insulation using the more complex expression taking into consideration the sequence between the convection and the conduction, where small h is different because the surface temperature is different. Should we need to comply with a specific heat loss, then we can use the expression in red saying what is the wanted thickness under a defined value of Q. Let's consider now another example. We look for the thickness of the insulation for a machine having an outer temperature of 200 degrees and a wanted temperature after insulation of 50 degrees. The temperature of the ambient stays as 20 degrees and the insulation property is 0.080 watt per meter per Kelvin. We assume to use our Conti Thermoprotect material. First of all, we need to determine the heat transfer coefficient, small h, by an empiric formula. The formula is linear versus delta T, and delta T is the temperature of the machine surface minus the temperature of the ambient. Turns into 22.19 watt per square meter per Kelvin for the not insulated machine and 10.13 for the insulated one. We notice that the surface temperature is very different in the two cases, because in one case the machine is not insulated and the second case is insulated. The heat lost by the machine before insulation is therefore easy to calculate and we get nearly 4000 watt per square meters. The insulation thickness needed to achieve Ts of 50 degrees is given by this formula and says 40 millimeters. The heat lost after the insulation is given by the same formula above, but with the corresponding values for the H and for the outer temperature, and therefore we get 309 watt per square meter. That is definitely 92% less. The last chapter tells the insulation for pipes, and here the loss formula is slightly different. It is considering the heat per unit of length instead of unit of area, and there are four parameters needed: the pipe diameter, the convection heat transfer small h, the inside temperature of the fluid, the ambient temperature. If the pipe is insulated, we need to introduce a fifth parameter, that is the insulation thickness, and therefore the external diameter is the internal diameter plus 2 times the thickness of the insulation. Only for calculation purpose, we define a third diameter, named transmission diameter. Its value is given by this formula, being the logarithmic average of the existing two, the internal and the external. The heat loss is the product of three factors: the pipe transmission area, the heat transfer coefficient, and the delta T, that is the temperature of the inside fluid minus the temperature of the ambient. The heat transfer coefficient is given by this relation, which takes into consideration that we have both conduction and convection, but they are taking place at different diameters. By writing the heat transfer formula between the insulated surface and the ambient, we can solve for the temperature of the insulation Ts, obtaining the expression in red. However, since H is also depending upon Ts, we need to solve this equation iteratively by starting from a guess value for Ts. Let's see now an example. We look for the insulation thickness of the steam pipe so that its surface stays below 45 degrees. The data are here displayed. How to solve? We need an iterative procedure. Let's start from a guess insulation thickness of 50 mm and we determine the external diameter with the formula that we have seen. Then we find also the transmission diameter by means of the found external one, and we calculate the convection heat coefficient small h, since the temperature of the surface is known and also the temperature of the ambient. Then we get the overall heat transfer coefficient capital HT, where all the remaining parameters are known, and we can find the heat loss per unit length of the insulated pipe by using this formula, where HT, DT, and the delta T is known, and we get 131 watt per meter. And by using the formula of the surface temperature, we find 47.1 degrees. That is eventually different from the starting 145. That means we need to increase the gas value of the thickness and repeat up to convergence when the Ts prime is equal to Ts. We find 56.5 millimeters rounded to 60. The heat loss when the pipe is not insulated would be given by this expression, where we have the diameter of the pipe, there is no insulation, the H prime is the convection coefficient, Te the internal temperature, and Tr the external one. And the convection coefficient is given by this expression, 22.19 watt per square meter per Kelvin. The saving versus the insulated pipe is 94%. To make your life easier, there exist many tools to make the automatic calculation of the thickness of an insulation. So do not be scared about the complexity of such a calculation. But as usual, I wanted to display you that to make you understand. And by the way, do you know that if we increase the pipe insulation too much, then the heat losses will also increase? See you next time.